So when looking at atomic spectroscopy, there's three common ways that atomic spectroscopy can be done, each slightly different in terms of the light source as well as what you're actually detecting. So I think the most common of the techniques, and the one that we have an instrument for this here at Connecticut College, is atomic absorption spectroscopy. So this works similarly to a UV vis absorption experiment, except for we don't have a cuvette and our light source is different as well. So we use a hollow cathode lamp to generate light. We'll get into what that is and how that works later in this chapter. Used to produce light, and we look at the atoms in our sample that are burned absorbing that light. Used to produce light, atoms in sample absorb. So if we sort of sketch out what a typical atomic absorption experiment looks like, we have our lamp here. It produces light, goes through our flame, and this is where our atoms of interest are. So those atoms will absorb some of the light, and then often the monochromator is after the flame instead of before it. You can have it in either place. And then we have a detector. So this will be a detector similar to the ones we've talked about previously. This is be like a photomultiplier tube or something like that. Okay, and so that's the basic idea. And so if we think about what's happening with the energy levels in the atoms that we're looking at, we have some ground state energy down here. These are excited levels up here. And in the process of the experiment, our atom is going to go from the ground state to one of these excited states. And that's what we're measuring, is the decrease in light. So if you want to get a background measurement, which you need to get the absorption, you run just a blank through your flame, usually just distill deionized water through your flame, and that's your blank measurement, and then you compare that to when you actually have your sample there. Okay, so that's the basic idea of atomic absorption. Our second option is atomic emission spectroscopy. And as you might expect from the name, here instead of a lamp, we have the light coming from our sample. Light comes from the atoms in our sample. Now these flames are hot enough that we can excite the electronic states of these atoms, and that allows us to then see the light that is emitted as they relax back down to the ground state. So light comes from the atoms that are thermally excited. Okay, so we have our flame, and our atoms are inside of it. There's no lamp here because this is an emission experiment, so the light is coming directly from, of course there's light from the flame, but there's light from the atoms inside the flame. We need a monochromator. And then we'll have our detector. So in some sense, it's a little bit simpler because you eliminate the lamp. Here, if we write out our energy levels, instead of the molecule starting in the ground state, it's going to, a lot of it's going to stay in the ground state, but we're looking at the molecules that have gone up to the excited state and then are emitting light as they come back down to the ground state. So there's no lamp or other light source needed. The final option that we have, and the one that's sort of most specialized, is atomic fluorescence. We won't spend a lot of time on this particular technique. It's because, as I said, it's much more specialized. But this is a fluorescence experiment. So our light source, we often have a laser. We usually use laser-induced fluorescence. So we're going to excite our sample atoms with a laser, then look at fluorescence emission. Let's see if I can spell fluorescence emission. Okay, and so we have our laser that comes in. We have our sample. Again, the same thing that's happening in all of these, that we're burning up our sample in some type of flame. And so these atoms are going to absorb the light, and then we look at the fluorescence here. Still need a monochromator. Still need a detector. But yeah, so this is a more specialized technique because the light from our laser has to match up with absorption of our atoms that we're trying to measure in the flame. So this is not as generalized. The atomic absorption and emission experiments will work for basically any atom. For the atomic absorption experiment, we need the proper lamp. Same thing here, you need the proper laser that'll work for the particular atom you're trying to measure. If we think about this in terms of the energy levels, just to complete this, we're first going to have absorption from our laser, and then we'll see the fluorescence. So maybe the molecule relaxes down to a lower state, but we see the fluorescence come out, and that's what we're looking for. One of the big advantages to doing this type of experiment is this can be very sensitive. Just like we've talked about previously with fluorescence experiments, fluorescence can be very sensitive. And most atoms, if you have them sort of by themselves like this, will fluoresce, which is a nice advantage. All right, so those are the three main types of atomic spectroscopy that you can do. We're going to focus mostly on the atomic absorption and atomic emission, but the atomic fluorescence is also an option.